Hi everyone, I'm trying to I'll start my name. My name is Mohammed Siddiq and I'm currently a PhD student in UK University, Center for Geoscience Computing, School of Earth Sciences. Actually, this work is supported by a Center for Coal Seam Gas, and I'm trying to present a new method to improve the processing on pre-stack seismic data. Actually, the main problem we face currently in coal seam is the seismic anisotropy within the coal seam, because coal seam layers, you can define it as strong anisotropy as it contains fractures, and the orientation of fractures is similar to VTI, and because of the dipping and the tilting, it could contain TTI type of anisotropy, and possibly HTI if we have a variation within the cool bed layers, because it's very thin cool bed layers. It's very thin. It's below seismic resolution. We can see here in this slide, we can see many authors actually start speaking about the strong relation between seismic anisotropy and the permeability. And it's quite logic, because if you speak about the reason of the anisotropy, can be related to presence of fractures or lateral variation of lithology, and all these parameters actually link it to permeability. So we can link anisotropy with permeability if this is the case. Also, we can define these orientational fractures if we can define accurately the anisotropy, because the velocity of seismic actually will be high as the same direction of the trend, as the same trend of the fracture, and it will be lower if it is perpendicular to the fracture trend. So by knowing the direction of high velocity and lower velocities, we can define somehow the orientation of fractures. What is important of defining anisotropy and hydrocarbonic separation? First of all, we try to get a good image, and of course, good image gives you good resolution and better seismic interpretation, and therefore reducing the risk of taking decisions that based on actually seismic interpretation. And if you link the anisotropy parameters with the fractures, orientation, and density, it can give you better reservoir characterization outputs. It will be more reasonable and more close to reality, of course. And it will reduce the cost of drilling. If you increase the drilling area of each well, eventually it will decrease the number of wells and therefore the cost of drilling. Okay, the main question is how actually we can define seismic anisotropy in our case. We developed a new method which is working automatically in isotropic and anisotropic media, and it gives you more information, as the output covers all the available offsets and azimuths within each CDB. And of course, it's faster compared to the conventional method. If we speak about the conventional method, we can mention semblance analysis. It can be automatically picked, but in isotropic case, you need also to pick the isotropic parameters. So it will be time consuming if you would like to pick the NMO and then pick the isotropic parameters and then correct your CDB. Actually, it will be time consuming, and the hardest part here, how actually you can define what type of anisotropy you are facing, because sometimes you need to correct for 3 types of anisotropy at the same time. And this is actually quite big assumption. If you assume that your data is TTI or HTI or VTI or thrombic media, still this is maybe close to your case, but still it's assumption. What we are trying to do here is to remove this assumption and work freely without even knowing what kind of azimuth type we are facing now. And based on our results, we have a good seismic resolution and better stack. We developed also a new method that can prevent the non-likeness problem that could be happen during the run of the automatic algorithm. How we test our method? 5 different tests. It's first with isotropic media, anisotropic media, or lateral heterogenic media. And of course, we use the VTI, famous HIS model from Graduate School of Mines, and one real called syngas, but I'm not going to show it in this video. And the last one is the online available data from Alaska in USA. The first one, test on isotropic media. The left side we can see the main CDB, how it looks like, and at the right side we can see the same CDB but in grayscale. We have the time and the offset. Here is just explanation what CDB actually means, but I will assume that most of the people actually watching this video knows what actually CDB means. Common depth point, which is this one. Okay. The output, how it looks like. The first one here is the non-corrected CDB, and the right side you can see the automatic corrected CDB, and you can see it's very good flattened, and actually it's automatic muted, started from point and ended by time. So we can compare this stacking of this CDB from the conventional and the automatic method. Actually, this may be not very important, but based on our results, we can see we have a better stack amplitude than the conventional method used from semblance. Here, test number 1, we can see how actually our velocity looks like. We can see here the velocity actually covers all our field or dimension. Like it's covered all the offsets all time instantaneously. At any point you can find a value for NMO velocity. And by only looking at this graph, you can tell what kind of media it is. You can see the velocity actually is very homogeneous, no big differences with offsets. So actually it looks like it's isotropic media, which is actually this is the case. The second test actually in anisotropic media, and why I'm calling it anisotropic media model, because if you look at the middle very thin layer, we're changing the values of densities and the velocities within this layer. It's not constant, it's changing with distance. So the density and the velocity is actually changing with distance, but for other layers we have constant density and velocity values. Here we can compare the synthetic CDB extracted from our model, and you can look at it like this. At the far left side, at the middle, we can see the semblance plot for this CDB and the NMO correction based on the picked velocities from the semblance. If you look at the corrected NMO from the semblance plot, we can see it's not flattened and actually have a curvy shape, which gives you very bad stack. Okay, I'll speak about these small 3 peaks in our CDB. Just you can consider it like an error from the routine program. It's not a big deal. The comparison between the conventional and the automatic NMO, here we can see the non-corrected CDB and the automatic corrected CDB and the conventional same CDB. You can tell by yourself the differences between the 3, how it looks like. And here, as I told you, the stacking from the conventional can show you we have 4 layers, but stacking from the conventional can be only 3 with low amplitude. Here is the velocity model from the extracted CDB. This output model actually looks very different from the isotropic case that as the first test we used. we can tell that the velocity actually changing with offset, and it's not homogeneous anymore just because it's very strong anisotropic media, or we can tell it's lateral heterogenic media, which is actually very hard to correct using the conventional methods. So this one gives you a good flattened, reasonable NMO velocity, and not only this, it can also give you information about the anisotropic effect directly from the velocity data. Not only we can define the horizontal anisotropy or instantaneous anisotropy, we can also define the vertical anisotropy, how it's changing with time vertically. Also, we can define more details from a single reflector. Here's third test is for HIS model, HTI, Brothers Group Mines. Here you can see the original synthetic data and the automatic corrected data. Let's see how the velocity looks like. Here you can see the maximum velocity we have is 7,000. Of course, this model is very famous, so you can easily tell that our velocity actually is very reasonable and within the range. By the way, if you look at the velocity field, I can tell that actually his model is very close to isotropic case. Actually, it's very weak anisotropic, and it's quite easy to work with this one. As you can see, it looks homogeneous and it's similar to the isotropic case, so I can tell easily that his model contains a very weak anisotropy. Here is the last test in Alaska, and we use pre-stack data. You can look at the middle, you can find the corrected one. At the far left is the main CDB, and also at the right is the original CDB, but at the left you can see it in gray scale. You can see our method actually gives a very good flatten, and here a comparison between the conventional semblance and the new automatic method. You can see the velocity field covers every single offset, and the same range. We can see the maximum range is 20,000, and you can see it's the same. So our estimation is actually very quite good, and it's within the range. Okay, thanks you for watching, and hopefully you can see any good comments from you. Thank you.